All right, homework handouts out, and kind of reviewing over the math from the chapter. There's a lot of terms, obviously, that you should have studied over last night. Things like uniform circular motion and centripetal acceleration and centripetal force and centrifugal force, periodic motion, oscillatory motion, simple harmonic motion, period, frequency, amplitude. I'm trying to think if there's any other. Restorative force, laws of the pendulum. What were those again? Give me one of them. Doesn't depend on the amplitude or the angle.
Or mass.
Doesn't depend on the mass.
Length.
Depends on the length. Square root of the length, technically, but depends on the length. That's the main thing.
Gravity.
Depends on gravity's acceleration. Inversely, square root, but depends on gravity. All right, so a lot of terms and stuff that you need to know. But this was reviewing the math. And the first problem says a girl rides on a Ferris wheel that moves at a constant speed of 3.0 meters per second. Now, it says constant speed, and that's the correct word to use, but we'll actually represent this class. V is the 3.0 meters per second, though it is not a constant velocity because you do have centripetal acceleration. That's what we're finding. It says the Ferris wheel has a diameter of 40 meters, but thoughts on the diameter, Kendall?
You need to split it in half.
We almost always need radii in problems. Now, we've looked at examples where, we might use diameters instead, but here I really do need the radius. 20 point meters. And it says, letter A, find the centripetal acceleration of the girl. Well, to find centripetal acceleration, I'll use the equation class.
V squared over R.
A sub c equals v squared over r. So we're going to square the 3 to get 9, divide that by 20, and we have 0.45 meters per second squared. Did we get that for our first answer? All right, the next thing says, find the force exerted on the girl if she has a mass of 28 kilograms. So as the Ferris wheel's going round and round, there are different forces keeping her moving in the circle. Could be the seat of the seat of the bench that she's riding in. Could be the back of the bench. Could be the crash bar. Could just be the friction force in most cases. It's not moving that fast. It's not like she's flying out. Good thing for the crash bar. I mean, seriously, have you ever needed the crash bar on a Ferris wheel? You probably held on to it, right? You would be really, really if it weren't there. But I mean, you don't need it. Anyway, probably it's just the friction of her own seat in most instances, or her own weight even, as she gets to the top of the Ferris wheel. But throughout, what is the centripetal force needed to keep her moving in that circle? In other words, what is the centripetal force? And for centripetal force, class?
MV squared over R.
MV squared over R. Or you could just say MA sub C, since we just found it. Now it tells us that the mass of the girl is 28 kilograms. So what I would do is I just take the 0.45, multiply that by the 28, and that gives us a force of 12.6, we'll round into 2 sig figs. 13 force? Newtons. 13 newtons. Questions on the second part of that first problem. All right, looking at the second problem, it says a 10 kilogram mass is hung from a vertical spring, and it stretches the spring 25 centimeters from its original position. Let's just stop there for a moment. 10 kilogram mass, which is a very large mass, stretches the spring. Thoughts on stretch? X is 25 centimeters, 0.250 meters, and from its original position. And when anytime I have the stretch is used, class, to find the spring constant. I'm going to find that spring constant using the equation
K equals
mg over x. So we'll take that 10, multiply by the 9.8, divide the 0.250. It didn't ask for it, but we had to find the spring constant to find the next part of the problem. At the end it says determine the period of oscillation. You have to know spring constant for that. What do we get for the spring constant, anyone?
392.
And I believe that came out evenly, if I'm not mistaken. 392 newtons per meter. It is 3 sig figs. You could also say kilograms per second squared, so either of those units would be acceptable. Not that either of those was the final answer anyway. That's on the path to getting the next thing. Once you've established the spring constant, it says we now replace that mass with a 15 kilogram mass, which obviously would stretch it further, but I don't care about that because I would just give me the spring constant again, right? Or I could find the stretch if I really cared. What I want to know is the period of oscillation. Period represented by capital T, period measured in seconds because it's time. How do I find the period of a spring?
2 pi square root of r.
Again, it's now a 15 kilogram object oscillating on a massive, thick spring with a spring constant of 392 newtons per meter. What do we get for the period of oscillation?
1.229.
1.229, blah, blah, blah. So when we do round off to our third sig fig,
1.23.
seconds. 1.23 seconds, our period of oscillation. Questions on the second problem? Feeling better about the quiz as we go on? Hopefully. All right, look at the next problem. We have a 5 Newton weight hung from a vertical spring, stretches the spring 8.5 centimeters. Number one, find the spring constant. Again, how do I find spring constant, class?
mg over x.
Mg over x. But what is mg, class?
Weight.
Weight. Yeah, mass times gravity, that's just weight. So really it's weight over x. It's just normally we're given a mass. Well, here I'm not given the mass, I'm given the weight. It's really 5 newtons. And I think it's 5.0 newtons for sig fig's sake. And it says it stretches the spring 8.5 centimeters. We have to do this every time, class. 0.085 meters. And so when we divide, number one, what do we get for that spring constant, Kendall? Oh.
I don't know the decimal.
Okay.
0.425.
5 divided by 0.085?
58.82.
There we go, 58.8, blah, blah, blah. We'll round off to only the 2 sig figs, so we'll say 59 newtons per meter, which is right in front of you, rather than kilograms per second squared, which is a little harder to extrapolate. But I would put this in the memory value of your calculator if you're redoing the calculation now. If you didn't get the 58.8, blah, 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 put it in the memory because you're going to need it here in just a moment. It says that this weight is then pulled down an additional 2.5 centimeters. And it says find the restorative force in the spring. How do we find restorative force? What is the restorative force, class? It's what counters the weight, correct? Now, if you pull on the weight, it counters the weight and you pulling, correct? So by pulling an extra distance, you've increased the restorative force. Remember, weight over x equals k. Therefore, weight would equal kx, right? That's Hooke's law. Tensile force, which is the weight on the spring, is kx. Restorative force then is negative kx. That goes back to chapter 5. We looked at it briefly. Haven't actually done a math problem with it, so I like that this is in here. Does that make sense? It's just going to be the opposite direction, so negative kx. Well, we know the k, that's that memory value, but it stretched the spring an additional 2.5 centimeters. Remember, it was already stretched 8.5 centimeters. How far is the spring stretched now? 11 centimeters, or 0.11 meters. So we're going to take our memory value times the 0.11 meters. How much restorative force is in that spring? Negative 6.47, blah, 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 round it off, we'll say negative 6.5 newtons. Now remember, there was only 5 newtons of weight down. So as soon as you let go, it says the weight is released, it begins oscillating. Why? Because when you let go, there's only 5 newtons down, there's 6.5 newtons shooting upward. So obviously, since there's an imbalance of forces, there's acceleration. If we wanted to, we could even find that initial acceleration upward. This won't be on the quiz, but let's do it. What is the sum of the forces in the y? 5 newtons down, and upward 6.5 newtons. 1.5 newtons upward, right? And to find acceleration in the y, we would take the sum of the forces in the y and divide by the mass. Now the only problem is I don't know the mass, I know the weight. So let's take the weight, 5 newtons, divide by gravity, 9.8. What's the mass of this object? 0.5102, blah, blah, blah. All right, put that in the second memory of your calculator. We won't need it past this point. Go and put that in the second memory of the calculator and divide 1.5 by that memory value. How rapidly is that mass going to accelerate upward?
2.94.
At 2.94, blah, blah, blah?
It's even.
Oh, two,
Yeah.
exactly?
Yeah.
Wow. So 2.94 meters per second squared upward will be the acceleration. All right, anyway, that's just kind of going full circle back to what we've been doing in the last chapter. So thought I'd throw that in there, make sure we don't forget all about how to find acceleration and net force and things like that. All right, but back to the problem. We've got this object and it's oscillating, right? It accelerates upward at 2.94 meters per second. Now again, as soon as it starts going up though, gravity is always pulling down. So it starts shooting up at that, but gravity's pulling down, so it slows until gravity stops it, and then it comes back down again, accelerating because of gravity until the restorative force decelerates it to stopping point. It just oscillates. The question is, what is the frequency of oscillation? How do I find frequency, class?
It's the reciprocal.
Reciprocal of period. Oh. Okay, how do I find period, class?
2 times square root of
And I told you you weren't going to need the mass past that problem, but it's a good thing it's in memory 2, isn't it? Hopefully you didn't clear it out already. All right, memory 2 is the mass which we found for the other problem. I forgot this was coming. And the spring constant is in memory 1. So you'll take that memory 2, divide by memory 1, take square root times 2 times pi. That gives you the period. That gives you this number. But I don't want that number. I want the frequency. So once I get the period, one more keystroke, reciprocal button. What do we get for the frequency of oscillation?
1.708.
Let's try this one. 1.70 blah blah blah, or 8, and is it 2 or 3? It's been 2 sig figs. Yeah, 2 sig figs this whole time. So we'll round it off and say,
1.7
and frequency measured in
hertz.
hertz per second, or hertz. All right, questions. Now, by the way, you could have gotten away with missing number 2. The restorative force didn't actually affect the next part, but we hadn't looked at restorative force yet, so this gave me a good chance to do that. Questions on problem number 3? All right. Ooh, I was about to say, let's move off of springs. No, we're not. One more with springs. Go ahead and read that problem while I erase the board, if you would, Michael.
An object is hung from a light spring with a spring constant of 7.35 newtons per meter. When set into motion, it makes 2.4 oscillations each second. What is the weight of the object?
All right. We know the spring constant, K. Oscillations per second. What is that, class? That's frequency. The frequency is 2.4 hertz, or oscillations per second. And it asks for the weight of the object. Well, how do I find weight, class?
10 times G.
Mass times gravity. Well, gravity, I'm good, right? So I know gravity is going to be the 9.80 meters per second squared. But what about the M? What about the mass? Kendall, what did you do? Cried? Besides that, once you were done crying and you said, no, I'm a senior, I can do this. Oh, you can't.
No.
Oh dear. Okay, Kendall. I've got a spring constant, and I've got a frequency, and really I need mass. I mean, it says find the weight, but if we get the mass, we've got the weight. So it really hinges on finding that mass. Is there an equation that relates mass, frequency, and spring constant? Not really, because frequency really isn't related to anything except for
The
period. Oh. But if the frequency is 2.4 hertz, then class, the period would be, find it, I don't actually have this written down. What would the period have to be, class? 0.416 repeating seconds. Oh, okay. Do I have an equation, Kendall, that relates mass, spring constant, and period? That I have. Do you see how to think through it? I need weight. What is weight? Mass times gravity. I need the mass. Huh? Well, frequency. All that is, oh, period. Right, so we could type this number. I don't know that we necessarily need to put it in memory. What equation relates these three, Kendall?
T equals 2 pi times the square root of mass.
And we've done this a number of times solving for the mass. We divide away the...
Divide 2 pi.
All right, so take the period, which is actually on your calculator. I guess you don't need a memory for that reason too. It's still on the calculator. Take the period, which is on the calculator, divide away the 2, divide away the pi. I just screwed it up. All right, so... All right, and then we need to square it, and then we need to multiply it by 7.35. And what? Ooh, this is a very small object. What's the mass? 0.032 blah blah blah. Did you get the 0.0323? Now that means it's only about 32 grams. It's a little bitty. This is a very light spring. This is about like my really, really small spring. So, about right. And it's oscillating very quickly. So it has to be a very small mass to oscillate quickly. Does that make sense? 2.4 oscillations every second. It's got to be a small mass. All right, so we take what's on the calculator now. That's our mass. It wanted weight multiplied by gravity. And how many newtons is the object?
0.316.
And round it off, I think it was 2 sig figs. Yes, so 0.32 is weight, so newtons. I think you might say newtons a second, but I don't remember. All right, questions on this problem? Do we see how to think it through? What do I need? How can I solve it? Almost feels a little bit like geometry class, doesn't it? What do I need to solve this? Well, I need this. Why can I get this? What if I found, I know that this gives me this. And all that geometry logic skill coming back. Love geometry. All right. What is it? Oh, somebody was asking a question after Bible the other day. It was your sister, and I think Josh was in there as well. And they were like, well, what about this answer? The question was, what command was given to Noah that had previously been given to Adam? And the answer was, be fruitful and multiply. And one student answered, replenish the earth. I said, wasn't that the same thing? I said, well, think about it. Replenish means to refill. Was Adam ever told to refill the earth? No, the earth hadn't been filled. The earth had been filled for Noah, so that's why he was told to replenish. But both Adam and Noah were told to be fruitful and multiply. So when you think about the definition of replenish, based on the definition of replenish, we can prove that he was not told to, it's like geometry class, and they ran out screaming. Okay, it wasn't quite that bad, but anyway, there was the comment, oh, it always goes back to geometry class. Anyway, great. All right, questions on springs. We've done 3 boxes of problems now dealing with springs. Questions on springs. Feel like you're going to be able to handle anything I throw at you now. All right, let's take a look at the last box, and pendulums are so much easier, or penduli. Find the period of a pendulum that's 45 centimeters long. How do I find the period of a pendulum, class? 2 pi times the square root of length over acceleration due to gravity. So in for the length, we plug in the 0.45 meters. In for g, since it didn't specify, we assume 9.80 meters per second squared. Pi takes square root times 2 times pi. Really straightforward. Kendall, you got?
29.
Oh. You didn't make it 0.45? I don't think so.
Oh, no, I don't.
I say. So, I was like, how did she get such a big answer?
That's fine.
That would be why. I also think you might have forgot to take the square root, but I could be wrong on that.
.045 newtons.
Well, and then times 2 and times pi. By the way, I'm not picking on Kendall. The other two had homework passes, so they didn't do the homework. So I had to rely on Kendall.
1.346.
At 1.34. Did it come out evenly?
No.
Dot seconds. Okay, and then but we're rounding off to 2 sig figs anyway, so
1.3.
1.3 seconds. Did you two get it now? All right. And let's see. Find the length of a pendulum that makes 27 oscillations each minute. Oscillations each minute, that's weird. We don't normally talk about oscillations each minute, class. We usually talk about oscillations per second. Oscillations per second is frequency, that's hertz, right? So what should I do with this 27 oscillations each minute? Divide it by 60. What is the frequency of oscillation for this particular pendulum?
2.2.
2.2 repeating?
Well, the frequency is 4.45.
You said it was what?
4.45.
0.45 hertz is the frequency. Now, the next question was going to be, does length relate to frequency directly? No, length relates to period. How do I find period? You ask Michael. He already did it. He got 2.2 seconds, repeating seconds for the period. And since I want to find the length, we'll do what we just did a minute ago. Divide the 2, divide the pi, take the, or square it, multiply by gravity. And, well, actually, we'll multiply by k on the last one, but multiply by gravity. And how long would this pendulum be?
1.22.
So round it off, we'll say 1.2 and length measured in meters. 1.2 meter long pendulum. And it's going back and forth 27 times in a minute. Questions on pendulums? Penduli. Any questions over chapter 10? Uniform circular motion, periodic oscillatory motion, especially talking with springs and pendulums. Any questions on the math? Any questions on terms? I threw out a whole litany of terms earlier as I was rattling off terms. Were you thinking of definitions or were you panicking? Michael's like, yes, panicking. Okay, which terms? Tell you what, I'll give you just a couple minutes to study. Take just a couple minutes to study while I erase the board, and then the quiz will be upon us. Quiz be upon you, Samson. I will shake myself as at other times. That's from the Bible. Well, I said it was Philistines, not quiz. Mike will be like, erase slower. Time has come. Clear thy desks. Set the pencil, paper, calculator. Make sure your memories are available. You want to clear those out so you don't accidentally use a value that isn't the right one. Better to have an empty memory that you forgot to store than something stored that you thought was right. So clear memories. First one's name at the top of your paper, along with today's date. Today is 11/16/22. 11/16/22. And this is quiz 13. Quiz 13. Let's take a look at the quiz together and then I'll let you get started. The top section, completion, write the word or words that best complete each of these statements. Number 11, short answer, so write 3 of those things. And then the problem solving. Number 12 and number 13 are connected. So 13 refers back to 12. So don't clear stuff after you finish 12. You may need stuff. 14 and 15 are also connected. So once you do stuff with 14, you're going to need to use that answer for 15. So again, don't clear stuff. And then 16 is a standalone problem. Any questions before you begin? All right, you may begin. For those watching, we can put the homework on the board, and we'll end the video here.